In this presentation, I'll go through some notes from Chapter 11 of book Designing Data-Intensive Applications. Chapter 11 is called Stream Processing. In this chapter, we have discussed event streams, what purposes they serve, and how to process them. In some ways, stream processing is very much like batch processing that we discussed in previous chapter, but done continuously on unbounded, that is never-ending streams rather than a fixed size input. From this perspective, message brokers and even event logs serve as the streaming equivalent of a file system. This chapter spent some time comparing two types of message brokers. The first is AMQP/JMS style message broker. In this class, the broker assigns individual messages to consumers, and consumers acknowledge individual messages when they have been successfully processed. Messages are deleted from the broker once they have been acknowledged. This approach is appropriate for an asynchronous form of RPC, for example in a task queue where the exact order of message processing is not important and where there is no need to go back and read old messages again after they have been processed. Log-based message broker. The broker assigns all messages in a partition to the same consumer node and always delivers messages in the same order. Parallelism is achieved through partitioning, and consumers track their progress by checkpointing the offset of the last message they have processed. The broker retains messages on disk, so it is possible to jump back and forth and reread old messages if necessary. The log-based approach has similarities to the replication logs found in databases and log structured storage engines. We saw this approach is especially appropriate for stream processing systems and consume input streams and generate derived state and derived output streams. In terms of where streams come from, we discussed several possibilities: user activity events, sensor providing periodic readings, and data feeds, that is market data in finance, are naturally represented as streams. We saw that it can be useful to think of the writes to a database as a stream. We can capture the change log, the history of all changes made to a database, either implicitly through change data capture or explicitly through event sourcing. Log compaction allows the stream to retain full copy of contents of a database. Representing databases as streams opens up powerful opportunities for integrating systems. You can keep derived data systems such as search indexes, caches, and analytics systems continually up to date by consuming the log of changes and applying them to derived system. You can even build fresh views onto existing data by starting from scratch and consuming the log of changes from the beginning all the way to the present. The facilities for maintaining state as streams and applying messages are also basis for techniques that enable stream joins and fault tolerance in various stream processing frameworks. We discussed several purposes of stream processing, including searching for event patterns, computing windowed aggregations, that is stream analytics, and keeping data systems up to date. We then discussed the difficulties of reasoning about time in stream processor, including the distinction between processing time and event timestamps, and the problem of dealing with straggler events that arrive after you thought your window was complete. We distinguish three types of joins in this chapter that may appear in stream processes. The first is stream joins. Both input streams consist of activity events, and the join operator stretches for related events that occur within the same window of time. For example, it may match two actions taken by the same user within 30 minutes of each other. The two join inputs may in fact be the same stream, that is a self-join, if you want to find related events within the one stream. Stream table join. One input stream consists of activity events, the other is a database change log. The change log keeps a local copy of database up to date. For each activity event, the join operator queries the database and outputs an enriched activity event. Table joins. Both input streams are database change logs. In this case, every change on one side is joined with the latest state of the other side. The result is a stream of changes to the materialized view of the join between the two tables. Finally, chapter discussed techniques of achieving fault tolerance and exactly one semantics in a stream processor. As with batch processing, we need to discard the partial output of any failed tasks. However, since a stream process is a long running and produces output continuously, we can't simply discard all output. Instead, a finer-grained recovery mechanisms can be used based on micro-batching, checkpointing, transactions, and idempotent writes. Here are some of the highlights. Within the publish-subscribe model, different systems take a wide range of approaches, and there is no one right answer for all purposes. To differentiate the systems, it is particularly helpful to ask the following two questions. What happens if the producer sends messages faster than the consumers can process them? Broadly speaking, there are three options. The system can drop messages, buffer messages in a queue, or apply back pressure, also known as flow control, that is blocking the producer from sending more messages. For example, Unix pipes and TCP uses back pressure. They have small fixed size buffers and it fills up, the sender is blocked until the recipient takes data out of the buffer. If the messages are buffered in a queue, it is important to understand what happens as that queue grows. Does the system crash if the queue no longer fits in memory, or does it write messages to disk? If so, how does the disk access affect the performance of the messaging system? What happens if nodes crash or temporarily go offline? Are there any messages lost? As with databases, durability may require some combination of writing to disk or a replication, which has a cost. If you can afford to sometimes lose messages, you can probably get higher throughput and lower latency on the same hardware. Databases usually keep data until it is explicitly deleted, whereas most message brokers automatically delete a message when it has been successfully delivered to its consumers. Such message brokers are not suitable for long-term data storage. Since they quickly delete messages, most message brokers assume that their worker set is fairly small and the queues are short. The broker needs to buffer a lot of messages because the consumers are slow. Each individual message takes longer to process and the overall throughput may degrade. Message brokers compared to databases. Databases often support secondary indexes and various ways of searching for data, while message brokers often support some way of subscribing to a subset of topics matching some pattern. The mechanisms are different, but both are essentially ways for a client to select the portion of the data it wants to know about. When querying a database, the result is typically based on a point-in-time snapshot of the data. If another client subsequently writes something to the database that changes the query result, the first client does not find out its prior result is outdated. That is, unless it repeats the query or polls for changes. By contrast, message brokers do not support arbitrary queries, but they do notify clients when the data changes. Multiple consumers. So, how can you support multiple consumers? There are a couple of approaches outlined in the chapter. One is load balancing. Each message is delivered to one of the consumers, so the consumers can share the work of processing the messages in the topic. The broker may assign messages to consumers arbitrarily. This pattern is useful when the messages are expensive to process, and so you want to be able to add consumers to parallelize the processing. Fanout. Each message is delivered to all consumers. Fanouts allow several independent consumers to each tune into the same broadcast of messages without affecting each other, the streaming equivalent of having different batch jobs that read the same input file. Similarly to change data capture, event sourcing involves storing all changes to the application state as a log of changing events. The biggest difference is that event sourcing applies the idea at a different level of abstraction. In change data capture, the application uses the database in a mutable way, updating and deleting records at will. The log of changes is extracted from the database at a low level. That is, example, by parsing the replication log, which ensures that the order of writes extracted from the database matches the order in which they were actually written, avoiding the race condition. The application writing to the database does not need to be aware of the CTC is occurring. In event sourcing, the application logic is explicitly built on the basis of immutable events that are written to event log. In this case, the event stories append only and updates or deletes are discouraged or prohibited. Events are designed to reflect things that happen at the application level rather than the low-level state changes. Processing systems. Broadly, there are three options to process streams. You can take the data in the events and write it to a database, cache or search index, or similar storage system from where it can be queried by other clients. You can push the events to users in some way, for example, sending email alerts, push notifications, or by streaming the events to a real-time dashboard where they are visualized. You can process one or more input streams to produce one or more output streams. A stream may go through a pipeline consisting of several such processing stages before they eventually end up at the output. Types of windows. Once you know how the timestamp of an event should be determined, the next step is to decide how windows over time period should be defined. The window can be used for aggregations, for example, to count events or to calculate the average of values within the window. Several types of windows are in common use. For example, tumbling window. A tumbling window has a fixed length and every event belongs to exactly one window. For example, if you have a 1 minute tumbling window, all the events within the timestamps between 10:03 to 10:03:59 are grouped into one window. Events from 10:04 to 10:04:59 in the next window, and so on. You could implement a 1-minute tumbling window by taking each event timestamp and rounding it to the nearest minute to determine the window that it belongs to. The hopping window. A hopping window, also has a fixed length, but allows windows to overlap in order to provide some smoothing. For example, a 5-minute window with a hop size of 1 would contain the events from 10:03 to 10:07:59. The next window would cover the events between 10:04 to 10:08:59 and so on. You can implement this hopping window by first calculating 1-minute tumbling windows and then aggregating over several adjacent windows. Sliding window. A sliding window contains all the events that occur within the same interval of each other. For example, a 5-minute sliding window would cover events at 10:03:39 and 10:08:12 because they are less than 5 minutes apart. Note that tumbling and hopping 5-minute windows would not have put these events in the same window as they have fixed boundaries. A sliding window can be implemented by keeping a buffer of events sorted by time and removing old events when they expire from the time window. Session windows. Unlike other windows, a session window has no fixed duration. Instead, it is defined by grouping together all events for the same user that occur closely together in time, and the window ends when the user has been inactive for some time. For example, if they have events for next 30 minutes. This concludes the Chapter 11 notes. Hope this was useful. Have a nice time. Like and subscribe for more such content.